Hey everybody, we're going to start chapter 7, and that tends to be one of the most difficult ones, so bear with me on this. As long as you put in the work and you practice, you'll have no problem with it at all. So basically where it starts is wanting us to find out equivalent trigonometric functions. So we want to find out 2 or 3 or 4 equations that are the same. So one way that we can do that, or the way that we're going to start, is by looking at the graph of trigonometric functions, so sinusoidal functions, so sine and cos functions, these waves that we see are on the left. So if I wanted to find out the equation for this, there's many different equations that we can come up with that will display this graph that we see on the left. So one of them is, if I was to look at it and see that this one cycle looks like this, you might say, well, that kind of looks like a sine function, because sine functions usually start on the x-axis. However, this one's going down when sine functions usually go up. So in order for it to start by going down means that the sine function must have been reflected. So one way that we can come up with an equation for this would be y is equal to negative sine theta. Right, just been reflected. So that's one equation to represent what we see here on the left. Well, let's think of another one. Well, let's think about sine again here. Let's suppose it started here. Maybe you see this function first. And you might say, well, that's a sine function. However, it's been translated to the left pi units. So if I wanted to write an expression for that, you might say y is equal to sine theta plus pi, because that would be shifting that to the left pi units. So that would display that equation we see there on the left. Maybe you look at this and say, well, I see a sine function that starts here, goes up, goes down, and it would continue for one full cycle. You might say, well, that sine function has been shifted to the right pi units. So another equation that we can come up with would be y is equal to sine theta minus pi. So I'll write that in there. So those are some possibilities. There's a lot more that you can come to. Maybe you look at this and say, well, I see it starts here, goes down and up. That's a sine function that's been flipped because it starts going down to its minimum. And you might say, well, that looks like it's been shifted to the left 2 pi. So you could have pi plus 2 pi. Might be another example. So these are all equations that represent the exact same graph. So these are all equivalent to each other. Is that it? No. There's a few more that we can come to that would be equivalent to that, and change color. There's also cosine. So one thing we know about cosine functions is that they either start at the maximum, like here, go down and return back to the maximum. So you might say, I see a cosine function here that has been shifted to the left pi over 2 units. So another equation for the exact same graph would be cosine theta plus pi over 2. So shifted that cosine to the left. So all those are equivalent, the red one and the 4 blue ones. You might say, well, let's keep going here. Maybe I see a cosine function that has been reflected, right? Starts down at the bottom, goes up, and it would continue down here. Now, if that's the case, I look at that cosine function and say, well, it's been shifted to the right pi over 2 units, but it's also been reflected because it's starting down at the bottom. So how would I write something like that? Well, it would look something like this. Y is equal to negative cosine, because it starts at its minimum. Right, I know it's been reflected. And it's been shifted to the right pi over 2 units, so pi minus, or theta minus pi over 2. And we get another one here. You could have another one that says, well, I'm going to start down at the bottom over here, so it's been reflected. Go up to its maximum. And in this case, it's been shifted to the left 3 pi over 2 units. So another one might be y is equal to negative cos theta plus 3 pi over 2. And there's an unlimited amount of equations that would display this exact same function that we see here on the left. Here's just 7 of them, just based on what we see here from negative 2 pi to positive 2 pi, right? And you can imagine these graphs continue on forever to the left and to the right. So there's an unlimited amount of equations that you can come up with from just a graph. So these are all equivalent to each other. How else can I get equivalent equations? Well, another way that we can think of finding equivalent equations would be like looking at the Cartesian grid and using our principal arm and our terminating arm. So one thing we know about our graphs are that if we have some value in the first quadrant, what I'm going to do is call the angle theta. So in the first quadrant, if we think about our three ratios, sine, cos, and tan, they're all positive in this quadrant. So let's suppose our terminating arm ended up here. So once again, our related acute angle is going to be that angle that's created down here. So what is the principal angle that we're talking about? How do I get what this big angle is going to be? Well, if I know right across is pi, I'm theta less than pi. So in order to get the angle that we have here, it would be pi minus theta. That'd be this angle right here. So let's come up with some expressions. So in quadrant 2, we have sine pi minus theta. I want to find an equivalent for cos pi minus theta and tan pi minus theta. If I want equivalent expressions to these, well, I know that in that second quadrant, only sine is positive, because remember the cast rule. Only sine is positive. So sine pi minus theta is equivalent to positive sine theta. Cos is negative in that quadrant. So cos pi minus theta is equivalent to negative cos theta. And tan pi minus theta is equivalent to negative tan, because tan is negative in that quadrant. So what does that mean? Well, let's take one of these ratios. Let's take sine, for example. Let's suppose the angle was 30 degrees, right, our theta. Well, or I guess it would be pi over 6 or 30 degrees if we were using degrees. If we think of this in terms of degrees, that's like 150. That's equivalent to sine 30, right? That's if theta was 30. Could be any acute angle, doesn't matter. So if I put in sine 150 in my calculator, I'm going to get the exact same expression if I put in sine 30. I'm just going to show you that here. So if I put in sine 150 is equal to 0.5. If I put in sine 30, I'm also going to get 0.5, those numbers that we see. Well, what happens with cos? If I put cos, 150, we get negative 0.866, right? That makes sense because cos in the second quadrant should be negative. That should be equivalent to the opposite, or the negative of cos 30. Notice that the values are exactly the same. The only difference is the cos for 150 is negative. So we said cos 150 was equal to the negative of cos 30. So if I go back, that's this expression here. We said cos of 150 is equal to the negative of cos 30. Cos 150 is equal to the negative, or the opposite, right, multiplied by negative 1, of cos 30. That's why they have different signs. And that would be the same for tan as well. So let's continue along here, just to get you the idea. We'll continue in quadrant 3. Now let's suppose we're here. We have our related acute angle, once again, is the angle that's created here, theta. But I want to know, what's the big angle that we have here? That's our principal angle. Well, in this case, once again, we know pi is right across the x-axis on the far left. So we're pi plus theta. So the big angle is pi plus theta. And we want to talk about how those ones work in quadrant 3. So we know that sine pi plus theta, cos pi plus theta, and tan pi plus theta. I want to find equivalent expressions for these ones. So in the third quadrant, I know tan is going to be negative, so it's equivalent to negative. I think I said tan's negative, but sine is negative in this quadrant, so it's equal to negative sine theta. Cos of pi plus theta is equal to negative cos, because cos is negative in the third quadrant, and tan is positive in the third quadrant, so it's equivalent to tan theta. So what does that mean? Well, that means if we have something like sine 200, that's equal to the opposite, or the negative, of sine 20. Right? Because the acute angle that we're talking about over here, if the acute angle was 20 degrees, that would mean our principal angle would be 200 degrees, because 180 plus 20. If our angle here was 40 degrees, well, then our principal angle would be 220. So sine 220 would equal negative sine 40. And those are equivalent expressions as well. And then finally, the last one we'll look at for quadrant 4, you're probably starting to get the idea here. Really, it's just using that cast rule. If we end up in the fourth quadrant with our angle that we have here, we might say, well, how do I get the angle for principal angle? Well, I know one full circle is 2 pi, but we're not one full circle. We're just short of one full circle. We're this section here short of one full circle, which is theta. So it's 2 pi minus theta. So I'm going to put those ones over here. So I want to know about sine 2 pi minus theta. I want to figure out an equivalent expression for cos 2 pi minus theta, and tan 2 pi minus theta. What are they equivalent to? Well, in the fourth quadrant, sine is negative, so it's equal to negative sine theta. Cos is positive, so it's positive cos theta. And tan is negative, negative tan theta. So these are equivalent expressions as well, right? Where theta is some acute angle between 0 and 90. So that's how I can use the grid to come up with some equivalent expressions as well. And let's continue down to the new part, cofunction identities. So what does cofunction mean? Basically what we're going to be doing is we're going to be not just going from above, we went from, let me show here, we went from sine to sine, cos to cos, tan to tan, always. Now we want to be looking at our sine and cos and see if we can interchange them. So what is the idea behind that? Well, if we have a right angle triangle like the one drawn on here, and we know our angle, in this case, instead of x, I'm going to call it theta, and we have 90 minus theta, right? That makes sense for any related acute angle. Like we know that one of the special triangles is 30, and if it's 90 minus 30, it's 90, 30, and 60. We know our special triangle as well. If one of our angles is 45, well, 90 minus 45 gives us the other 45. And it doesn't just have to be special triangles. I could have an angle of, let's say, 20 degrees. Then it'd be 70 up here, right? Because there's only 180 degrees to go around, and we've used up 90 here. So between the two angles, there's only 90 to go around. So these two values have to add up to 90. Right? We know that we have 30 and 60, we have 45, 45 triangles. Those are special triangles. So what I want to do is come up with the ratios for each of them. So remember the side lengths are just the lowercase of the opposite angle. That was stuff from grade 10. Right, B is opposite angle B, A is opposite angle A, and lowercase c is opposite angle C. So if I want to come up with some equivalent expressions, well, let's start with ones that we know. I want to know what sine theta is. Once again, I'm going to call this theta as opposed to x. I want to know what cos theta is, tan theta is. Well, sine I know is opposite over hypotenuse. So opposite is b, hypotenuse is a, so this is b over a. Cos is adjacent over hypotenuse, so in this case it would be c over a. And tan is opposite over adjacent, so it's b over c. So that's great. Now let's look at the other angle that we know. So instead of us looking at theta, we're going to look at the 90 degree minus theta. Or you might say pi over 2 minus theta, right, if we're using radians. Maybe we'll continue with radians, I guess. Let's see what sine pi over 2 minus theta is. Let's see what cos pi over 2 minus theta is. And tan pi over 2 minus theta. That's just the other angle that we're talking about, right? Theta is the angle that's in the bottom left-hand corner of our triangle. And pi over 2 minus theta is the angle that's in the top corner of our triangle. So let's see what those are equal to. So sine is opposite over hypotenuse. So in this case, our opposite is c, hypotenuse is a. Cos b over a. And tan is equal to opposite over adjacent, so c over b. So looking at what these are equal to, do I see any that are equal to each other? Because that would give us a co-function identity. Well, you might look at it and say, well, these two are equivalent. They're both equal to b over a, no matter what. So that's our first one. Our co-function identity says sine theta is equal to cos pi over 2 minus theta. What else do we notice? Well, I see that these two are equal to each other. So I know that cos theta is equal to sine pi over 2 minus theta. They're equivalent. And lastly, you might look at this and say, this is not really the same as this, but they have the same letters. I notice that the one on the left has b over c, and the one on the right has c over b, so it's the reciprocal. So, what would make it b over c? If I took this one over here, I'm going to do a little side note here. I know that tan, well, the reciprocal of that is cotangent of that same angle, would be equal to b over c, which is tan theta. Now they match. So tan's not equal to tan, tan's equal to cotangent. So I'm going to write that one down. So tan theta is equal to cotangent of the other angle that makes up 90 degrees. So here's some more equivalent expressions for trigonometry ratios. So we have lots of them. So one way that you might be able to think about, well, how is this one going to be useful? What I want to do is show you a little trick on a grid for something like that. So I'll try to display this as best I can on this grid here. Let's suppose that we have a terminal arm that's in the first quadrant. And we have a related acute angle. We're going to call it theta. So what do I know about this compared to our co-function identities? Like, let's suppose I want to know, well, what's sine theta and cosine theta equal to? Well, let's take this quadrant. If I know up here is pi over 2, I know that the angle that's created in here has got to be pi over 2 minus theta. Right? Why does that make sense? Well, if I think of it in terms of degrees, up here we have 90 degrees. Let's suppose our angle was, I don't know, let's say 40 degrees, for example. That would mean the angle that we have up here is 50 degrees. Right? It would be 90 minus 40, which is 50 degrees. Right? They have to add up to 90 degrees. So that's that 90 minus theta, 90 minus our related acute angle. That's how we get that value. So I know that for our original triangle that we have, I'm going to erase our values because we're not going to use those. I'm just going to think of it as theta and pi over 2 minus theta. For original triangle, let's take sine, for example. Sine would be the opposite. This is my y value, right? Because I'm going up on the grid. Sine is equal to y over hypotenuse, which is my r, my radius. Let's look at our other angle here and see what is y over r. Well, I'm going to make this triangle here. Let's use a different color. Sorry, I'm changing colors a lot here, but let's imagine we have a triangle here. Purple one. What side of this triangle would be considered y? Well, that would be this side over here because it's how much we're going up from the origin. That'd be the adjacent side. What side's r? Well, it's still the radius over here. So to get y over r, I would have to be the adjacent side over the hypotenuse. Well, adjacent side over hypotenuse is cosine of pi over 2 minus theta. That's what we came up with. That was one of our identities that we made here, the first one. Well, what about cosine? Well, let me erase what we've got here. Well, cosine of theta is what? Well, I'll use red here again. Cosine is the adjacent side. Well, that's the x value because that's how far we go to the left or to the right over our hypotenuse, right? Our value here. So that's really like x over r, which we already knew that was. So let's take our pi over 2 minus theta to figure out what is the x value, what's the r value in that purple triangle. Well, the x value would be the side over here. The r value is still the same, the diagonal. So what is that from that angle pi over 2? Well, it would be the opposite side over the radius. Not radius, the hypotenuse, r. Opposite over hypotenuse, well, that's sine pi over 2 minus theta. So it kind of breaks down to the exact same thing that we found in that triangle above. Because at the end of the day, when I look at this triangle that we have, sine of this angle, b over a, is the exact same as cosine of this angle, b over a. That's really what it comes down to. So anytime we get an angle that's up here, not a related acute angle, I can use the cofunction identity in order to write it in terms of our related acute angle. So if I had a question, I might say, well, what is sine 90 minus theta equal to? Well, what angle are we talking about, 90 minus theta? Well, that's telling me that we're given this angle here would be 90 minus theta because theta is the related acute angle. Well, that's got to be equivalent to cosine theta. And we can test that. Let's actually think of if theta was a number. Let's suppose theta was 22. That would say, well, sine 90 minus 22 is equal to cos 22. Well, sine, when I subtract those, 68 is equal to cos 22. So if I put in my calculator sine 28 or 68, I should get the exact same answer as I get for cos 22. So sine 68, I get 0.927. And if I put in cos 22, I get the exact same answer. So that's using that cofunction identity. So I can get the same value between sine and cos based on that, these three in red here. We can go between them. That's why it's cofunction, because co means two. So we're going between two different functions. So one last thing. All right, and lastly, just a quick tie-in with odd and even functions from earlier chapters. If you remember, even functions had the property that if I had f of negative x, that was equivalent to f of x. Right? If I substitute a negative x, all the negatives would work out to be the exact same as the original function. If we had an odd function, we knew that f of negative x was equal to negative f of x, right? Just the opposite of the original function. So let's look at sine and cos. If you remember, sine looks something like this. And we said, well, what kind of graph is sine? Well, sine theta is an odd function. Can I tell that from the graph? Well, I know that it has that rotational symmetry. Remember, if I took this graph and I flipped it 180 degrees, right, rotated it around the origin, I would end up with the original graph, right? That rotational symmetry that we talked about. So what does that mean? Since sine theta is an odd function, I know that sine of negative theta should be equal to negative sine theta, right? That's just this property up here. Now, are those equal to each other? Well, I can put those into my calculator and try for some values. I'm going to take this off here for a sec. I can put in my calculator sine of negative 22, and I should get negative sine 22. I don't even need to put that in my calculator to check it, because what does that mean? Sine of negative 22 means that it's gone, negative angle tells me it's gone clockwise, 22 degrees. I know that that's in the fourth quadrant, CAST. I know that's equivalent to the negative, because it's in the fourth quadrant, sine's negative in the fourth quadrant, of sine of that related acute angle, 22. So I already know that these are the same. You can put them into your calculator and test it if you want, but that's one way to think about how it relates to odd and even. So I'm going to leave that one up there. Let's look at cosine. Cosine graph starts at its maximum, goes down, but then it does that in the opposite direction as well. So you might say, what type of function is this? Well, we might remember that cosine is even, or is an even function. Why? Because it's reflected about the y-axis, right? It's the exact same on the left side and right side cosine function. So because it's even, that means that cos of negative x should be equal to cos of x. That's that top property that we have. Now, does that make sense? Well, let's erase this and go back to our original grid that I talked about with the plane. I don't know why I put x. I'm going to make these thetas. But imagine that we have cos of negative, tells me we're going in this direction, clockwise, with a related acute angle of theta. And because that's in the fourth quadrant, I know that cos is positive in that quadrant because of the CAST rule, C-A-S-T. So that would tell me that cos of negative theta should be the exact same as cos of theta, right? Because cos is positive in that quadrant. So that's kind of how those apply. These aren't brand new. We have these ones up above, but that's kind of the idea behind our finding equivalent trig functions. There's lots of different ways that you can do it, but the idea is that there's not just one expression to represent one trig function. And that's that. If there's any questions, let me know. There's a couple questions in the book for you to